Okay. The first thing, oh, it plays music through this. Log properties. This is essentially what we're working with. They can work to either Okay, so I'm just going to kind of explain what these properties are. Basically, if we start on the left side where we're taking a log of multiple terms or multiple things, we can expand those terms to be multiple logs. So one thing that we're going to do as we go through the examples is when we see a single log, we're going to ask ourselves, we're taking the log of how many terms? If it's 2 terms, that means we should have 2 logs when expanded. If we're taking a log of 3 terms, that means we should have 3 logs when expanded. Okay, so however many things we're taking a log of is how many new logs we should have when expanding. And you'll notice that based on what we're taking a log of tells us how they will expand. So if we're multiplying the terms that we're taking the logs of, we're going to add the 2 logs as we expand them. If we're dividing the terms, then we're going to subtract those logs. And then this last one is if we have a power or an exponent for what we're taking the log of, that exponent can also move and become the coefficient on the log itself. So this last one would read log base b of m to the power of p. And when we expand it, it then becomes p times log base b of m. Okay, so we're going to start by working on the left side, going from a single log and expanding them out. And then after that, we're going to take a expanded log and work on condensing it down to a single log. So we're going to work in both directions here. Okay, and that's why it kind of makes sense to teach these together. Now, before we do this, just another reminder, kind of like what I gave on the warm-up, to a really important exponent property that's going to show up multiple times when we expand and condense logs. So we have the nth root of x, that is the same thing as taking x to the power of 1 over n. That's where we get that fractional exponent. So an example that we've already seen is if I have the cube root of x, that's equal x to the 1/3 power. So whenever we're taking roots, think fractional exponents. Now, another one that can be kind of tricky here is if we have a root, the nth root, of some value raised to an exponent. So if I have the nth root of x to the power of m, that can be rewritten as x to the power of m divided by n. So the exponent becomes the numerator, and the value of our roots, or whatever root we're taking, is the denominator. We should see that consistency here, okay? That whatever we're taking the root of will always be the value of our denominator. So an example of this is, let's say we have the cube root of x squared. So kind of like what we had in this other example I made here. It's just instead of it being 1/3, now it's x to the power of 2/3. Okay, so that's a really important property that's going to show up as we expand and work to condense logs. Okay, so we're essentially going to go through each property just one by one before we throw in multiple properties at once. But that's essentially what we're working towards. We're getting a log where there's lots of things we're taking logs of and being able to expand those out and apply all those properties. All right, so in part A, and I'm going to do both of these here, A and B for us. But in part A, one thing that's important to take note of before we expand this out, I'm asking myself, I'm taking a log of how many terms? Well, technically it's only 1, right? Because 7 times 5 is 35. But we're going to practice this to expand it. So I'm essentially telling myself, I'm taking a log of 2 terms, of 7 times 5. So when I expand this out, I should have 2 new logs. The base is going to stay the same. And since I'm multiplying what I'm taking the log of, I'm going to add those two new logs. So it's log base 4 of 7 plus log base 4 of 5. And that's it. Okay, that has been expanded out. Now, one thing that we should check for is like the warm-up. Are there any logs that can be evaluated to equal a whole number or a nice number? So when I get here, I'm going to ask myself, 4 to what power is 7? If it's not a whole number or a fraction or a negative number, we're going to leave it as is. Okay, so 4 to the power of what is 7? I have no idea, right? 1 point something. So we're not going to evaluate that and write it as an actual value. We're only going to do it if it works out to be a nice number. Same thing with 4 to the power of what is 5? I don't know, some fraction or decimal as well, right? So this is actually expanded and simplified. Now in part B, remember that if there is no base written underneath the log, it's assumed to be base 10. Now for some of us, it might make sense to actually fill that base in there. Now one thing I'm noticing here is I have 10x, so those are two terms, so I should have two logs when I expand this out, where it's log of 10 plus log of x. Now here's why I think it might be helpful for us to fill in the base sometimes. I know that even though I don't see a base, it's a base 10. And so when I fill this base 10 in, it allows me to go into a headspace where I'm like 10 to the power of what is 10? That would be 1, right? 10 to the power of 1 is still 10. So this actually simplifies to 1 plus log of x, or 1 plus log base 10 of x. And I believe MathXL would accept either answer. If it would be picky, it'd be picky and accept that answer. But I think either one should be okay there. Just a reminder that when there's no base, it's base 10. And everyone's seeing how this is 1 and where that's coming from? I'm going to check for that. Okay, I would always check for those. And again, we're only going to evaluate it if it's a whole number, a fraction, or a negative value. All right. We're going to move on to the next rule, covering the quotient rule. I'm going to do part A and then have you all try part B. And so in this case, I have log base 7 of 19 over x. Since I'm taking the log of two terms, I'm expecting this to expand out and have two new logs that are going to be subtracted since we are dividing the terms for what we're taking the log of. So this is log base 7 of 19 minus log base 7 of x. I am going to check if I can take 7 to some power to get 19. Not any power that I can think of. It would be some long decimal. So that is considered expanded and simplified. All right. Why don't you all try part B? We'll go through part B in just a second. All right. So here's our expanded form. First thing that I think most of us should be able to get without much issue is just applying the property, where this becomes natural log of e cubed minus natural log of 7. Okay, that's just us simply applying the property, the quotient property there. But then we've got to think about, do either of these logs simplify down? Well, here's what we need to remember. This natural log of e cubed, sorry, it's frozen there for a second. Over here, we wrote natural log as log base e of e to the power of 3. Now, you have in your notes that when we're taking a log of something that is the same thing as the base, and it's raised to an exponent, it ends up just equaling the exponent. And the reason that is because of some of these properties we're learning today. And so I went ahead and basically this is what we should have known walking into today. If you studied or looked at some of the properties that are already in your notes, that as soon as we see this, it's just whatever the exponent is. Now the reason for that is when we have an exponent for what we're taking a log of, that exponent becomes the coefficient. And so this becomes 3 times log base e of e. Log base e of e is just simply 1. In fact, when we take the log of anything, that's the same thing as the base. It'll always be 1. So it's 3 times 1, which is just 3. And so the simplified expanded version here is 3 minus the natural log of 7. Okay, these parts where it works out to be a nice number, it's always going to be a little sneaky, okay, especially depending on the form there. All right, I think any questions here before we move on to the last property, which we essentially just used? Okay, we're all good here? Okay. All right, and I'll do A, then I'll have you all do B and C. For part A, I'm looking at this and I notice that there is an exponent on what I'm taking the log of. That exponent being 4, that's going to bump down and become the coefficient. So this is really 4 log base 5 of 7. And that's it. I can't simplify that any further. There 5 to some decimal power is 7, but that's not a decimal that I know off the top of my head. So real quick, why don't you all try B and C? See what you come up with. So part B, that brings in the square root, which means we have a fractional exponent. And so you're going to see this written in 2 different ways. The way that I would expect most of us to write it is to take that exponent of 1/2 and just make it the coefficient. So 1/2 natural log of x. But you're actually going to see it written more times as natural log of x divided by 2. And these are the exact same thing. When you think about what 1/2 natural log of x is, that's really 1/2 times the natural log of x. And so when I multiply 1/2 times natural log of x, I multiply the numerators together, so 1 times natural log of x, and the denominators together, so 2 times 1. And that's why these are the exact same thing. Okay. Also, another way is this is dividing by 2, this is multiplying by 1/2, accomplishing the exact same thing, right? Any questions here on B with that square root of x? All right, then in part C, with this 5, my instinct is to just make that the coefficient like the property says, but then I'm still taking the log of 4x, which are 2 terms. So that can expand out to be 2 new logs. And so the question is, what do we do with the 5? Does it follow and become the coefficient on both logs? And the answer is yes. Okay, so this is 5 log 4 plus log, or plus 5 log of x. Now, here's another explanation or a reason why that 5 kind of follows both logs as the coefficient. When you think about 4x to the power of 5, what that really means, right? It means 4x times another 4x 5 different times. So really, this ends up being 4 to the 5th and x to the 5th. And so when you apply these properties, the 4 to the 5th and x to the 5th, you see that the exponent of 5 is being applied to both the 4 and the x, and thus it is the coefficient on both of those logs there. Okay, so a couple different ways of how you can think about that and eventually lead to this simplified expanded log here. Okay, so the next thing we're going to do is we've covered kind of all the basics of the properties, and now we're going to apply multiple properties at once to try to ultimately expand this log as much as we can, right? And I'm going to, actually, I'll go ahead and do A and then have you all do B. So a lot of times you might have different ways of getting to this expanded log, okay? There's not going to be like one clear-cut way to get there. So I just always start with, okay, what do I recognize and what are some things that I can do? Well, I recognize that I really have 2 terms here, right? I'm taking the log of x squared and root y. So I'm going to have 2 logs as I expand this out. So this becomes log base b of x squared. Since those things are being multiplied, I'm going to add the logs. So plus log base b of root y. So then again, I'm like, okay, what do I know that I can do? I know that the exponent of 2 can become the coefficient, making this 2 log base b of x. And then I know that root y, that's really y to the 1/2. So that really ends up making this 1/2 log base b of y. And another way that you could write this is 2 log base b of x plus log base b of y, which is getting divided by 2. Either answer is going to work there. Math Excel will take either answer there also. All right, why don't you all try B, and I'm going to warn you right now, B is a little tricky, mostly in terms of what the signs are in front of the logs. All right, give you about a minute or so to try B. All right, so there's a few tricky things here. Again, I think it's a good idea for us when we first see the log to think about how many different terms are we taking the log of, and thus that gives me an idea of how many logs I should have at the end. Well, I see a root or a cube root of x of 36 and a y to the 4th, leading me to conclude there should be 3 logs when I expand them out. Now, when I first expand the division into 2 logs that are being subtracted, it's log base 6 of cube root of x, and then minus log base 6 of what the denominator is, which is 36y to the 4th. Now, 36y to the 4th, those are going to expand out even further. Okay, those are 2 terms. The 36 and the y to the 4th are not stuck to each other. And so using the parentheses here can be a really helpful way to keep track of all these signs and what this ultimately ends up simplifying to. Now, I use big brackets. It's just an easier way to keep kind of the organizational there. You can use normal parentheses. There is actually no difference when we're using brackets or parentheses to kind of organize our work like this. So then I'm like, I can take the cube root of x, write that as x to the 1/3, and I can expand this out where it is log base 6 of 36 times log base 6 of y to the 4th. That then allows me to conclude that log base 6 of 36 is 2, right? 6 squared is 36, that's why this is 2. And then the exponent of 4 becomes the coefficient. And since I'm subtracting both of those terms and they are in parentheses, I'm essentially needing to distribute this negative, which brings us to our final expanded log, which is 1/3 log base 6 of x minus 2 minus 4 log base 6 of y. Now, one thing that you're going to pick up on is anytime a term is negative, that's going to, when we, let's say, condense these, those terms should be in the denominator. So since this was really negative log base 6 of 36, I'm like, okay, 36 is going to be in the denominator. Since it's minus 4 log base 6 of y, y to the 4th is going to be in the denominator. Okay, so anytime the log is negative, if we're condensing it, think about that term ending up in the denominator. Is everyone following what I'm saying there? Okay, we're going to get another example like that here in just a moment as well. Okay, so questions here, because this is kind of us using all the properties. Yeah?
How did you get
The 2, I'm just evaluating what log base 6 of 36 is by thinking about 6 to the power of what is 36. 6 just like kind of what we did in the warm-up. To close these notes out, we're just the process where I'm going to give us logs that are already expanded, and we're going to work to condense them. And the properties are the exact same. So if you look back to the properties you wrote down to start class, we were first going from the left side of those properties to the right side. Okay, and now we're going to go from the right side to the left side. And again, referring back to those notes you took right at the beginning. So I'm looking at this, and I notice that I'm adding 2 logs together. If I want to condense that down, and before I even work through that, know that when we are condensing the logs, you should only write log 1 time. Okay, and I've seen so many times that when we go to combine them and condense them, people are still writing logs all over the place. Okay, we want to write it as a single log. So I'm going to start with just log. I'm like, okay, the base is 4. And then since I'm adding these logs, when I condense them, I'm going to multiply when I'm taking the log up. So 2 times 32. Yeah?
You only expand and condense logs with the same base.
Correct. The bases need to be the same. I'm going to show us a way how we can change bases here in a second. So we'll talk about that. Now, it's a good idea just to make sure that this might simplify. So I know 2 times 32 is 64. And by doing that, I'm actually able to recognize that this log evaluates to be a whole number. And I'm figuring that out by thinking 4 to the power of what is 64? That'd be 4 to the power of 3. That's not one that a lot of us know off the top of our heads. It's kind of where a calculator can be helpful. Okay, but 4 to the power of 3 is 64. So this whole thing just simply equals 3. And that's it. Yeah, was it?
Could you and I mean, it's a lot easier to do it that way, but could you just solve each one and then add them together?
Yeah.
That would be more complicated.
Yeah, yeah. Right, because this would have been 1/2. This would have been 6. No. No. No.
Oh, you can't? Okay.
That's something completely different, right? Ooh. You can. This, evaluating this one, log base 4 of 32 is going to be some fraction. Kind of a tricky way to get to that. Okay, in theory, the answer is yes, but I don't know that it would be the best way to solve this one here. Okay. All right, part B. Same idea. This time I'm noticing the logs are being subtracted, so when I condense them, I should see division. And so it is the log of the first term, 4x minus 3, divided by the second term, x. Okay, and that's it. Nothing more that we can do. Some people are wanting to cancel out these x's. Remember, that can only happen if everything is completely factored and the factors are the same. So in order for this x in the denominator to cancel out, we would need this to show up, so 4x minus 3, with another x being multiplied to all that. Then these x's can divide out, because x divided by x is 1. But 4 times x divided by x, and that 4x we're subtracting 3 from it, it does not cancel. Okay, so don't cancel that x and that x. We would need another x for those to completely cancel. Okay, I'm going to have you all try some of these condensing, and it's going to involve multiple properties. And I'll give you a few minutes to do so. Why don't we say 4 minutes to work through A, B, and C. And we'll go through all 3 of those. And then we have one last quick thing to close out these notes. And the rest of the time will be your time to work on Math Excel. A and B, as A and B are a little bit more straightforward than C. So for A, and I really want to emphasize, especially as we use multiple properties here, when you are condensing or even expanding, just do one thing at a time. Okay? When you're learning how to do these, don't try and go from expanded log to condensed log in one go. Do one thing at a time and be like, okay, what can I do with this? So I first noticed that I have these coefficients. The coefficients can always move to become exponents. And that's all I did in step 1. Then I'm like, okay, can I rewrite any of those exponents as a different term? Well, x to the 1/2 is the same thing as the square root of x. And that's all that I did there, which then allowed me to see that the last thing I'm going to do is take the 2 logs, since they're being added, combine them, and multiply what I'm taking the logs of. So it's log of root x times x minus 1 to the power of 4. Nothing more that we can do there. Okay, that is completely simplified and condensed down. So in part B, the idea is the exact same. What can I do to start? I can take that coefficient of 3, I can make it the exponent. So that's x plus 7 cubed minus natural log of x. This time I'm recognizing that the natural logs are being subtracted. And so when I condense these, I should see division. Now, notice I'm not writing like the division symbol like this, right? We are always going to write it as a fraction. Fractions are just division. Okay, that's a more formal way to write these than using this division symbol. So it's just x plus 7 cubed divided by x. The placement of that exponent is important. If it was on the outside of these bigger parentheses, it would be completely different there. Okay, so that 3 needs to only be applied to the x plus 7, okay, and not anywhere else. All right, so anyone have questions on A or B there before we jump into the harder one, C? Okay, part C. Once again, what can I do? The first thing I can do is take all of the coefficients and make them exponents. So it's x to the 4th, 6 squared, and y to the 1/2. Then I'm like, all right, well, can I rewrite any of those terms? And the answer is yes. Right? I can rewrite 6 squared as 36, and I can rewrite y to the 1/2 as the square root of y. Then I'm also recognizing that both of these logs are negative, thus allowing me to factor out a negative. And so that's what you're seeing from this first step to the second step, that I am factoring out a negative, and by doing so, I am actually adding these last two logs together. That's what's going to help me keep track of which terms end up in the denominator and which terms end up in the numerator. So then, log base b of 36 plus log base b of root y combine together to be log base b of 36 times root y. And since it's one log minus the other, it ends up combining to be log base b of x to the 4th divided by 36 root y. Now, again, going back to what I said on that other example that was kind of complicated. Any log that is negative, those terms are going to end up in the denominator. So as you get the hang of this, as you do more problems, you're going to automatically go x to the 4th numerator, 6 squared denominator, y to the 1/2 denominator. Okay, you don't need to actually show all of these steps. I show these steps more so that we can kind of see where all of these terms go. All right, so this is way more work than needs to be shown, more of an explanation in the work. Might be a good idea for some of us to start there, but as you get the hang of it, any that's negative ends up in the denominator. All right, questions here on part C. I just got one last thing for us after this. All good? Okay. So the last thing in the notes here is what's called the change of base property. And the main use for this actually relates back to calculators that did not have the ability to change bases. Now, some of you are already picking up on the fact that you can probably take your graphing calculator and there is a way to change the base to be whatever you want, but I don't want us doing that. Okay, eventually I'll let you do it, but right now I don't want us doing that. Okay, old calculators did not have that option. Old calculators, you could only type in log base 10 or natural log, which is log base e. So to evaluate logs, we needed to use this change of base property. This also has some helpful, we're going to see this again when we actually start to solve log equations. So there's more than one use. So basically this is saying if we have log base b of m, we can change it to be log base a, where a is any value that we want it to be. It can be any base. So log base a of m divided by log base a of b. And typically, we're not going to pick just any random base. Almost always, we're going to choose log base 10, so we're going to call it log of m over log of b, or natural log of m divided by natural log of b. So how I remember this is when I'm taking a log and I need to use the change of base formula, I know that it's going to turn into division, where it's the log of what I'm taking the log of, so log of m, divided by the log of the base. B, I'm like, okay, base goes to the bottom. That's how I remember it. Base to the bottom. So just real quickly to put that to use, if I have log base 5 of 140, I can rewrite that as log of 140 divided by log of 5. Or natural log of 140 and natural log of 5. All of those are going to equal the exact same value, which I'll just show that to us real fast. Okay, and again, the reason we're choosing log base 10 and natural log is because just about every calculator has a log base 10 and a natural log button. And so those are easily accessible. So I can do log of 140 divided by log of 5 which is 3.07. And just to prove my point, natural log of 140 divided by natural log of 5 is the exact same value, 3.07. Okay. On Math Excel, it'll tell you how many decimal places to round to, so make sure you're reading that part before you submit your answers. All right. That is it for today. The rest of the time is your time to work on Math Excel.